Hello students, and welcome to section 2-1, Inductive Reasoning and Conjecture. So making conjectures. Inductive reasoning is reasoning that uses information from different examples to form a conclusion or statement called a conjecture. I wanted to continue on those two ideas in the following way. So I have a page that is, as you see, entitled Patterns in Inductive Reasoning off to the side. In daily life, you frequently look at several specific situations and reach a general conclusion based on these cases. For example, you might receive excellent service in a restaurant several times and conclude that the service will be good each time you return. This type of reasoning, in which you look for a pattern and then make an educated guess based on the pattern, is called inductive reasoning. The educated guess based on these facts is called a conjecture. Not all conjectures are true. When you find an example that shows that the conjecture is false, this is an example of a counterexample. We will be primarily dealing with inductive reasoning in our discussion here today. However, there is also something called deductive reasoning, where instead of going from something that's specific to something that's general, in deductive reasoning, you go in the other direction. So you start with a general idea and you narrow it down to something specific. Inductive reasoning is much harder because you go from specific to general. I will be honest, most professions that have information that is not quite yet solved, like for example, or facts, that don't quite yet put them in a position to solve a problem, like for example a doctor, a lawyer, or even the criminal justice folks, the police departments. They use inductive reasoning all the time because they start with something specific and their goal is to get to a general solution. So we're going to go ahead and talk about how inductive reasoning and how conjectures fit into our analysis for today. Later we'll discuss deductive reasoning, like I said. Example 1. Write a conjecture or an educated guess about the next number in the sequence, 1, 3, 9, 27, 81. So here what we're going to do is we're just going to look for the pattern. As you can see, from one number to the next, it appears that each number is a power of 3. In other words, 3 to the 0, that's 1. 3 to the first, 3. 3 to the second, 9. 3 to the third, 27. 3 to the fourth, 81. So the conjecture is that the next number will be 3 to the fifth, or 243. Again, we took specific information and we put it into a general case, of which you can see right here, the power of 3, each number raised to the power of 3. So there's your conjecture. Example 2. Write a conjecture about the number of small squares in the next figure. So again, we want to look at the specific cases and we want to generalize to get our conjecture. Again, our educated guess. So looking for a pattern, the sides of the squares have measures of 1, 2, and 3 units. So 1, 2, 3 units. The next, I would argue, pretty obviously would be what? Would be four-sided. Would be a four-sided square. So it would be what? 16 small square units if you were to kind of draw that out and look at each respective square on its own. Moving on. So we're going to write a conjecture that describes the pattern in each sequence, then use your conjecture to find the next item in the sequence. So -5, 10, -20, -40. If you look, it appears that you're multiplying by -2 from one term to the next. So there is your pattern. The conjecture, of course, then would be what? -80. So taking the specific numbers and generalizing with multiplication to get your conjecture. Inductive reasoning is very, very important, as you can tell. Number 2, 1, 10, 100, 1,000. It appears we're multiplying by 10 to get each next term in the sequence here. So I would argue if you multiply by 10 again, you're seeing here hopefully as the answer speaks to 10,000. Number 3, 1, 6/5, 7/5, 8/5, and then I'm saying here a 9/5 because it looks like you're adding a fifth, and that's the case. Make sure you're in fact seeing the same exact number being added or multiplied, or even in some cases subtracted or divided. Write a conjecture about each value or geometric relationship. So for number 4, they give you 3 points. We're going to plot A, which is -1, -1, B, which is 2, 2, and C, which is 4, 4. So there's your 3 points. Okay, here's A, here's B, here's C. I would argue that if you were to maybe try to draw a line through all 3, which you can, it is proving here that you have collinear points. And if you recall, collinear means same line. So all 3 points fall on the same line. They're collinear. So that's the conjecture. Number 5, angle 1 and angle 2 form a right angle. Okay, here's angle 1, here's angle 2, and there's your right angle. So the conjecture is that angle 1 and angle 2 are complementary angles. Number 6, angle ABC and angle DBE are vertical angles, and you can see I've even marked them up as you should also with regards to congruency, and that's the statement that I'm finalizing with for my conjecture. Angle ABC is congruent to angle DBE, and the reason again is because they're vertical. Number 7, angle E and angle F are right angles. Here's angle E, right angle. Here's angle F, right angle. Similar to number 6, the argument will be then that angle E is congruent to angle F. So your final conjecture is just that. Let's move on. So finding counterexamples. A conjecture is false if there is even one situation in which the conjecture is not true. The false example is called a counterexample. So here we go. Example. Find a counterexample to show that the conjecture is false. So if segment AB is congruent to segment BC, and you could see that because this is 3 and this is 3, then B is the midpoint of AC. Now as it turns out, the way that this picture is drawn, it's very clear that these segments are not combined in such a way where all 3 points are collinear. I could have drawn point A, B, and C on the same line so that they were collinear, and yes, then this statement would technically be true. But here's what they say. Is it possible to draw a diagram with AB congruent to BC such that B is not the midpoint? This diagram is a counterexample, as you can tell, because point B is not on segment AC. So certainly the conjecture is false. Point A, B, and C are not collinear. So this is a good counterexample. In other words, this now has to be false because this particular example is really, of course, disproving that statement. All right, let's move on. Determine whether each conjecture is true or false. If it's false, give a counterexample. Okay. I'm also going to draw pictures if it's true, just to help you understand generally how it should look. Number 1, if points A, B, and C are collinear, then AB plus BC equals AC. Okay, so all 3 of your points are in fact collinear. Question is, again, is AB plus BC equal to AC? Well, here's AB, here's BC, and just by that fact alone, well, this segment must be, the way I've drawn it, must be equal to AC plus BC. In other words, C, because it's in between these two, it doesn't allow you to look at this equation and, for example, suggest that AC is equal to AB plus BC. This statement is not true now. And if you were to plug in a number like, how about, I don't know, let's say this is 1 and this is 2, then the whole thing would be 3. Okay? The equation doesn't make sense then, because AB would be 3, BC would be 2, and no, 3 plus 2 is not equal to 1, because, well, obviously 3 plus 2, and not just the picture, but the math proves out that it's 5. So the answer is false. C could be between A and B. Now, if you thought of putting B between the A and C points, that's a true statement, right? But because there's a counterexample, in other words, I can put C in the middle, and this then all of a sudden is not a true statement. So of course, overall, we say that this statement is false. So even one counterexample makes the statement false. Number 2, if angle R and S are supplementary, and angle R and angle T are supplementary, then angle T and angle S are congruent. Okay, so R and S. Note that this is obtuse, and I try to make this look acute, but also if you were to make them added together in a sense, or make them adjacent even, where they're touching one another, certainly you've got 180 degrees, I would argue, the way that I've drawn them. Okay, they add to 180. R and T are supplements, so look at these two angles. So that angle plus that angle also would add up to 180. Because we're trying to finalize the conclusion of which angle T and S are congruent, well, of course they have to be, right? Angle T and S must be congruent if these two add to 180 together, and separately those two add to 180. Okay, if this was 150, for example, this would be 30. And again, 150, this would be 30. So both of these obviously must be 30. So this is not a counterexample. It's just proving that it's a true statement, and there's no depiction that I can create that makes this false. All right, this is a good picture that, again, just suggests that it's always true. There is no counterexample. Number 3, if angle ABC and angle DEF are supplementary, then angle ABC and angle DEF form a linear pair. Again, I've tried to draw this in such a way where this is obtuse, this is acute. If you add these two angles together, I would argue you get 180. I purposefully wrote them or drew them out in such a way where they're not touching one another. So in this case, this is your counterexample. The answer is false. And the reason is that the angles could be non-adjacent. So this picture is showing that the angles don't actually touch each other. They're not sharing a side or a ray. And because they're not adjacent, but they're still supplements, then this overall is technically a false statement. Again, the counterexample makes it false. Could you draw a picture of which the angles are touching each other and make them look like they're a linear pair? Well, yes. But again, if you could even think of one example that makes it false, which is what I drew for you here, then the whole thing is false. Number 4, if DE is perpendicular to EF, and this should be a segment, so I'll go ahead and I'll erase the arrows later for you. If segment DE is perpendicular, to segment EF, then angle DEF is a right angle. Well, that's the very definition of perpendicular, right? If you have a perpendicular relationship, certainly you've created a right angle here with angle DEF. So the answer is true. There is no counterexample that can disprove this. In general, if you guys can think through how different pictures are going to take shape, I think this right here, this example, is a great example of which, yeah, you might be able to draw one case that's making this particular statement true, but can you envision and then can you draw a picture that is slightly different that, of course, is making the statement false? So you're thinking of a counterexample when you're doing these problems.